Industrial organizations routinely invest tens of millions of dollars into enterprise asset management software to oversee complex machinery. Yet the actual operation of these assets often depends on undocumented duct tape solutions. In the field, this looks like technicians hunting through storage bins for unlisted parts, or overwriting formal protocols just to keep a production line moving. Traditionally, management views these moments as a failure of discipline, a gap in training, or simple human error. But that perspective overlooks a deeper structural pattern. These operational workarounds act as the final, visible signal of a data architecture collapse occurring far upstream from the factory floor. To understand why a technician is forced to improvise, we have to look past the physical machinery and examine the invisible data structures that dictate how the plant operates. This pyramid maps the hierarchy of maintenance failure. The workaround is the visible peak. Beneath it lies a lack of data ownership, unclear rules, and poor structure, the root causes. Banning workarounds fails. They return because the flawed foundation remains. To eliminate the workaround, we have to trace the symptom backward to its exact genesis in the workflow. We can isolate the point of failure by tracking the microscopic level of the daily maintenance workflow. This sequence maps the asset information needed to complete a single job: planning, scheduling, execution, closeout, and finally, reliability analysis. If we inject weak data, like an inaccurate bill of materials, into the first planning stage, the entire chain reacts. Scheduling is instantly compromised because the baseline data regarding parts and labor is false. The process breaks at execution. Lacking the correct parts or specifications, the technician is forced to invent a workaround on the spot just to complete the repair. This unrecorded improvisation is then captured as corrupted data during the closeout process. This corrupted feedback loop permanently blinds the organization's reliability analysis, making it impossible to accurately predict or prevent future failures. If the daily workflow is broken from the start, we have to look further back to see where that bad planning data originated. This requires moving beyond daily operations to look at the multi-decade lifespan of the physical asset. An asset moves through 5 macro stages, from the initial project and commissioning, into operations and modifications, and eventually to retirement. During the initial project phase, technical information, like engineering drawings and preventive maintenance strategies, is generated in a pristine state. The success of the asset's entire operational life depends on how these data packets are handed off between these stages. The most dangerous handoff occurs during the transition from commissioning to operations. At this stage, massive volumes of disorganized contractor data are often dumped onto the operational team in a rush to start production. Without strict governance, critical specifications literally fall out of the system due to mismatched formatting and compressed timelines. Operations ends up inheriting an incomplete baseline of the asset they are now responsible for maintaining. This data deficit ensures that the daily planning workflows starts with weak information that makes workarounds inevitable. Many organizations try to fix this deficit through brute force data cleansing projects. However, information that is merely clean often creates a false sense of security. This Venn diagram shows the true standard for asset information. Clean data simply means the spelling and formats are standardized. It looks good on a spreadsheet, but that is only the first step. The second requirement is that the data must be correct. It must perfectly match the physical reality of the asset on the plant floor. Clean data that is factually wrong will still lead to a maintenance failure. Finally, the data must be structured. It needs a relational map so the maintenance software can logically connect parts to machines and schedules to people. Accurate operational decisions are only possible in this exact intersection: trusted maintenance information. Anything outside this center is just organized noise, incapable of supporting a technician in the field. To reach that center point, the organization needs a mechanism to process the noise. At the top of the decision funnel, we have a chaotic flood of raw data coming from sensors, manuals, and legacy systems. The standards of clean, correct, and structured act as a filter within this funnel. This process distills the raw chaos into a narrow stream of knowledge that a technician can actually use to execute a job. Strict architectural governance is the only way to convert a messy asset history into a reliable physical action. When this data architecture is sound, the impact on the factory floor is immediate. Trusted information allows the asset baseline to cross from commissioning to operations with complete integrity. This ensures the daily planning workflow starts with the correct parts. Because planning is accurate, execution becomes flawless, and the technician no longer has to improvise. By addressing the data foundation, the operational symptom of the workaround is eliminated at the source. Management cannot simply mandate an end to workarounds through memos or disciplinary action. Human improvisation will always step in to fill the physical gaps left behind by a lack of structural data ownership. High-performing reliability teams distinguish themselves by acting as data architects first and maintenance executors second. True reliability comes from ruthlessly fixing the root causes in the data structure, rather than policing the symptoms on the floor. Leading organizations govern asset information with the same engineering rigor they apply to the physical machines themselves.